Good day everyone. This video is a continuation of my lecture on measurable set. Now let us recall first that when a subset of a set of real number A is measurable if and only if we have this equality. Now let's have here let's define this class of sets. We have this is the class of measurable sets, script M. Now in lemma 1.14, if we have two measurable sets, E1 and E sub 2, then their union is also measurable. So the union of the two measurable sets is also measurable. Now to prove this lemma, we use the measurability of the two sets. So in that case, we will use that the Lebesgue outer measure of A is equal to the Lebesgue outer measure of the intersection of A and E1 plus the Lebesgue outer measure of the intersection of A and the complement of E1, and the same with E sub 2. And we will show that for any subset of R, that the outer measure of A is equal to this one, because we want to show that E1 union E2 is measurable. So instead of writing E, we have here E1 union E2. Then plus the outer measure of A intersection of the complement of the union of E1 and E2. So we want to show this one to prove lemma 1.14. Now, here in corollary 1.15, the class of all measurable sets is an algebra of subsets of R. Now let's try to recall the conditions of being an algebra of subsets of R. So these are the conditions of the algebra of sets. We have here script A is the class of sets, which is an algebra if and only if the two conditions here are satisfied. The first condition is if two sets are in the class, then it should be that their union should be in the class, or it is closed under finite union. And then here, it is closed under complementation. It means if the set is in the class, then its complement is also in the class. So hence, for the class of measurable sets, it should be that it is closed under finite union and under complementation. So we only show there two conditions. Now here, for this class to be an algebra, it should be closed under finite union and complementation. Now lemma 1.14 shows that this class of all measurable sets, is closed under finite union. So we have here by lemma 1.14 and by remark 1.12, this second remark here states that if E is measurable, then its complement is also measurable. So it shows that our class of measurable sets is closed under complementation. And so, by lemma 1.14 and remark 1.12, we can say that the class of all measurable sets is an algebra of subsets of R. Now let's have here lemma 1.16. We let here A be any subset of R, and we have here a class of E1, E2, and up to E sub n. We have here a finite disjoint family of members of our class. So it means these are all measurable sets. Then we have here our equality. To prove this result, we use mathematical induction. So let's have here corollary 1.17. So we have here the set of measurable sets, the class rather of measurable sets. Then we have this equality here. To prove this, we used lemma 1.16. So by letting A equals R, the set of real numbers. So let's have this one. So we let A be equal to the set of real numbers. So we will replace A by R. We have this. And summation where I is from 1 to n. Now in this case, the intersection of any set to R is of course the set, because R is our universal set here, or bigger set. So therefore we have here the intersection is just equal to the union of E sub I, where I is from 1 to n, which is equal to the summation of the outer measure of course, the intersection of R and E sub I is E sub I. So where I is from 1 to n. So we have shown this equality here by using lemma 1.16 and letting A be equal to R. In this theorem, states that the class of measurable sets is a sigma algebra. Now let's try to recall what is a sigma algebra. Here, an algebra of subsets of X is a sigma algebra if it is closed under countable unions. That is, we have a sequence here of sets in script M, which is a sigma algebra. Then we will show that its countable union is in script M. Now to prove this one, we use corollary 1.15. We show first that it is an algebra of sets. We also use this proposition, this one. We also use lemma 1.14 and lemma 1.16 to show that the sequence of measurable sets is also measurable. So in that case, after using all those results and some concepts, we can show that the class of measurable sets is a sigma algebra. Next is, we will show that this open interval here is a measurable set for all A and for all real number A. So to prove this one, we let A1, here A1, this set A1 be equal to this A intersection this set, and A set 2 is A intersection, what's this set? This set actually is the complement of the given set. Now recall that E is measurable if and only if the Lebesgue outer measure of A being subset of R, here, intersection E. So, Lebesgue outer measure of the intersection of A and E being measurable, and then here, intersection of A and its complement of the, we want to show the set being a measurable set. Now here, since we want to show that this is measurable, so it means we replace E by this set and its complement. Now take note here that this is A intersection the set we need to show being measurable set, this one, and A2 is A, this one, it's the complement of the set given. So hence, if we want to show that this set is measurable, so we just get the sum of the Lebesgue outer measure of the two sets here. So this is the same as this condition. So as you noticed here, we will show that the outer measure, Lebesgue outer measure of A is greater than or equal to the sum of the Lebesgue outer measure of the two sets. Now notice that we can still show greater than or equal. We have it in our remark na pwede equality, we can treat equality, or we can show ito lang greater than, because we have shown already less than or equal, that it always follows. So that's it in this lemma. For the next, we have every Borel set is measurable. In particular, open and closed sets are measurable. Now to prove this result, we will show this one. So take note, this is a symbol for Borel set. And to prove this, we show first, of course, this script M here is a sigma algebra. Because we know that this is a sigma algebra. So it suffices to show then that this script M here contains every open subset of R. So we have here the Borel sets. So that's it. So this is all about measurable sets. Now in my next video, I will discuss their Lebesgue measure. So this will be my discussion for our next topic. Okay, thank you for watching and listening.